So before we go into the rest of 4.8, I want to address one more example. This was one that I'm out of practice enough. I had to kind of examine it carefully, look up a couple of strategies because it really messed with my head how to take its antiderivative. So I'll give you the function, and let's look at it in pieces. So when I first looked at this, I'm kind of strategizing in my head a little bit what I'm going to do. And I know that the denominator, that 1 plus x squared, is generally a tan inverse situation. Because let's see, antiderivative of 1 over 1 plus x squared becomes tan inverse. So I kind of had that in my head, and I thought maybe what I could do is I could split this into 2 over 1 plus x squared and x squared over 1 plus x squared. And I figured I could make this, when I take the antiderivative, make that 2 tan inverse of x. And that part's true. The problem is I don't have anything I can really do with that. The tan inverse doesn't have an x squared in the top. I can't take the antiderivative of them separately. So I was kind of stuck. So I looked up some strategies and realized that there's a simpler step here. So tan inverse is still going to be involved, but it's a little bit different. The correct strategy instead is to take out a 1. That seems weird. So first I'm gonna take this in very small steps. Okay, I'm gonna split that 2 into 2 pieces, quite literally. And then what I'm gonna do is I'm gonna separate my fraction into 1 over 1 plus x squared and 1 plus x squared over 1 plus x squared. So that's a step I just don't normally think of that. I don't normally think of splitting that constant into multiple pieces. But that's perfectly logical, perfectly legal for you to do. And so we should see from here how it gets fairly simple. This piece is just equal to 1. And so its antiderivative is going to be x. And as we already said, the antiderivative of this piece is tan inverse x. So for our most general antiderivative, we get tan inverse of x plus c. Okay? Which reminds me, we forgot to put the plus c on the last one. So we got to be careful of that. Even I forget sometimes. So whenever it's a general antiderivative, you have to add on that constant. So that was just a kind of a weird one that I saw and I wanted to walk through because you're going to see different problems you have to take antiderivatives of, and I want you to see multiple strategies. Any questions? All right, let's take a look at example 4 in the notes. So example 4, instead of starting with the derivative, we start with the second derivative, which means we have to take the antiderivative twice. Now, taking the antiderivative twice is akin to taking the derivative twice. You're using the same procedure, just 2 times. And if we want to find a particular antiderivative from the second derivative, then we typically need 2 points. And you'll see why here in a second when we get to our general antiderivative. So the first step is to find the first antiderivative. So if we're given f double prime, we need to find f prime. So what is the antiderivative of 12x squared? 4x cubed. Okay? So again, we're raising the exponent by 1. And so we've got to multiply out front by 1/3, which brings 12 to 4. Okay? So the next step is similar. Okay? If we're taking the antiderivative of 6x, that x has got to go up 1 degree, makes it to x squared. So we're multiplying the 6 by 1/2, which gives us 3. And the minus 4 gets an x tacked on. Right now it's got an x to the 0, if you will. And so we're adding 1 to it and multiplying by 1/1. It's the same rule, just we don't think about it normally because of the because it's so basic to add it to a constant. So since we only have an antiderivative at this point, what else do we have to tag on to the end of this equation? Plus c. We've got to add a plus c to the general antiderivative. Okay? It's our constant making its way in. All right. So take just a minute, probably only 30 seconds, and see if we can at least come up with the antiderivative of these first 3 terms. Do that real quick on your own. All right, so piece by piece, what's the antiderivative of 4x cubed?
X to the 4th.
X to the 4th. That exponent goes up by 1, okay, to 4, and we multiply by 1/4. All right, somebody from Sackets, what's the antiderivative of 3x squared? X to the 3rd. Okay? Exponent up by 1, multiply by 1/3. What's the minus 4x going to be, Antonio? Negative 2x squared. Now, here's the key. We've got that constant added in the end. So if we take the integral or the antiderivative of a constant, we get the constant times x. Now we have to add in a new constant because we have a new constant at this step. And chances are high that the two constants are not the same. Okay? So generally what we do if we add a c at the first step, the next step we add a d. You can do C1 and C2 if you want. We need something to differentiate them because they're not almost never the same constant. There'll be some special cases where it is, but almost never the same constant. So here's why we need two given values. We have two unknowns. So we need two values to establish two equations. So we could plug those in. We know that f of 0 equals 4. So 4 equals 0 plus 0 minus 2 times 0 plus c times 0 plus d. So for this one, it should be pretty obvious that d is 4. When they give you f of 0, that's always a pretty easy one. Now that we know that d is 4, we can use the other point to find c. So if we have f of 1, if we plug 1 in for x, we get 1 out. So we got 1 to the 4th and 1 cubed minus 2 times 1 plus c times 1 plus d, which we now know is 4. Now, this one that they set up for you is fairly easy. Nice, neat numbers. Not a whole lot of work, but quite often you're going to end up with two equations with a c and a d in them. And you got to solve them just like you would solve any system of linear equations. Okay, substitution, elimination, what have you. So if you're rusty on those skills, you're going to want to make sure you brush up on them. But like I said, this one's fairly straightforward. 1 equals, that cancels out. We got c plus 4. So c equals negative 3. So we have our particular antiderivative, and we can write it all as 1. Or what you can do is just go back and replace c now with -3 and d with 4. And there's our particular antiderivative. That is f. Okay. So the key is to make sure you throw in different constants at different steps. Any questions on this problem? All right. So one of the main applications, or at least early applications of the antiderivative, is in something called rectilinear motion. Can't even pronounce it today. Antidifferentiation is particularly useful in analyzing the motion of an object moving in a straight line. Recall that if the object has position function s equals f of t, then the velocity is v equals the s primed of t. The velocity is the derivative of the position function. That means that the position function is the antiderivative of the velocity function. So just to sketch that out, just to make sure we got it, if s is our position function, then velocity is its derivative, and acceleration is the second derivative of s, or the first derivative of v. Which means we can use the antiderivative to go in the opposite direction. So this is the process of differentiation, working from the position function to the acceleration function. Working from the acceleration function up to the position function is antidifferentiation. Okay? So when we know something about its acceleration and velocity, we can work backwards to find its position, which is what we're going to do here in example 5. So we know a of t, they give us the acceleration function is 6t plus 4. So if we know a of t, we have the second derivative of the position function. So we could also write, instead of just a of t, we could write s double prime of t. So we want to work backwards, just like we did in that last example. We want to work up to the original function from its second derivative. So we start by taking the antiderivative of the acceleration function. So that will give us the velocity function. What's the antiderivative of 6t?
T squared.
3t squared. What's the antiderivative of 4? Four t. Okay, and as usual, since we're just at the general antiderivative step, we've got to throw in a constant. Now, what we could do is we could do the antiderivative here and get right to the position equation, but I think it's a good idea here to pause and look at what our initial velocity is. So it gives us our initial velocity is -6, so we can figure out what c is before we move on and save ourselves a little bit of work. So since v of 0 equals -6, what does C equal? -6. So now I can work off of that for my acceleration equation. So acceleration, or sorry, I'm backwards. I started with acceleration. I'm working towards my position equation. Got in the habit of going the other direction. So my position equation is going to be the antiderivative of that equation. Somebody from Sackets, what's the antiderivative of 3t squared? T to the third. All right. Joe, I haven't heard from you in a while. You're kind of hiding off screen there. What's the antiderivative of 4t? Two t squared. We're going to bump that t up by 1, multiply by the reciprocal of the new exponent. All right. Eric, what's that -6 become? -6t. All right, and then we've got another constant in there, so we could throw a d in. Okay? You could throw d, c, b, whatever you want. We don't want to use c because that's already taken care of, but in general, it doesn't matter which letter you use. Don't use a variable you've already got. Don't use another constant you've already got. So last step is to take our last piece of information there. It's initial displacement. S of 0 equals 9. The nice thing is when they're giving us this S of 0 equals, that's essentially your constant. I mean, you can do it out and check it. And every once in a while you'll have something weird. Like if there was an e to the x in there, when you put in a 0, it's going to give you a 1. So that will throw it off a little bit. But barring some weird addition into the function there, you're going to have your d there is 9. Okay? So that gives us our final equation. If we go back and replace that d with 9, we have our position equation. Any questions on that problem? All right, we got one more example for this chapter. We'll do a couple of practice problems coming out of that, and maybe we'll get out early. See? So, similar type situation. Ball is thrown upward with a speed of 48 feet per second from the edge of a cliff 432 feet above the ground. Find its height above the ground t seconds later. When does it reach its maximum height, and when does it hit the ground? Now, if you're looking at this with fresh eyes, you're probably thinking there's quite a bit of information missing. We want to work back to, if we want to know its maximum height, we're going to need to know the position equation. And we know that the position equation is the second antiderivative of the acceleration equation. The problem is we don't have an acceleration equation. We could use our, what's the word I'm looking for? Vertical motion model. That's a good step. But in this one, I like to demonstrate how the vertical motion model is derived from the acceleration issue. So the first thing that we have to understand is a particular constant. The acceleration due to gravity. Now, first of all, gravity pulls you, generally speaking, in a downward direction. Okay, it's a negative mode of travel usually. Every once in a while, we'll orient things so that up is negative and down is positive. But in general, down is negative. And the acceleration due to gravity is -32 feet per second, or feet per second squared. Now, it's also equal to negative 9.8 meters per second squared. Okay? That's a helpful number, not for this problem, but in general. The reason I know I'm not using it in this problem is because everything I have is feet or feet per second. So I want my acceleration to be in those units as well. But if they give you a problem with meters or centimeters for height, then you want to start with the negative 9.8. So we're going to work our way back to our position equation, and we're going to start to see where our position equation comes from. Our vertical motion model comes directly from this number right here. So v of t has got to be the antiderivative of the acceleration function. Now we know if we start with negative 32, we're going to tack on a variable there for the antiderivative, and we have to throw in a constant. Now that constant we can find because we know its initial velocity or its initial speed. That is our constant. So at time 0, okay, if 0 goes in for t, we get a velocity of 48. Since it's thrown upward, that velocity is positive. Okay, if it was thrown downward, the velocity would be negative. Okay. So since that ball is thrown upward, we're going to have a positive 48 there, which means our c is, of course, 48. So we have our velocity equation. And when we take the antiderivative of that, we're going to get our position equation. So we should understand by now the antiderivative of negative 32t, that exponent's going up by 1, brings it up to 2. So I've got to multiply by the reciprocal of 2, which brings negative 32 to negative 16. I've got to add a t to the 48, and then I've got another constant. I'm going to call it b this time, just to change things up. And so our last piece of information is going to tell us what that is. Our initial height, where the ball is thrown from. So at time 0, the ball is at a height of 432. So b is 432. So my equation, my position function, is s of t equals negative 16 t squared plus 48 t plus 432. So before we look at the actual question itself and determine whether or not we've answered it, I want to point something out. When you were given the vertical motion model for the first time in probably Algebra 1, you were basically given as negative 16 t squared plus v naught t plus h naught equals s. So your position equals negative 16 t squared plus initial velocity plus times t plus initial height. Okay? And so we just worked through how to get that, where that function comes from, using anti-differentiation starting just with the constant of gravity. So whoever came up with that model started with the constant of acceleration due to gravity and worked backwards. And that's how we got our position function, or our vertical motion model. Any questions yet? We haven't answered the problem yet, but any questions yet? All right, so as for answering the questions, the first part of it is done. The function itself is the is the height above the ground t seconds later. It's a function based on time. So whatever t you plug in gives you the height. The second question is, when does it reach its maximum height? Now, if this was thrown downward, we'd have our maximum height already. If it was actually propelled in a downward motion, we'd have our maximum height because it would be at its highest point when we released it. But it's not. It's thrown upwards, so we have to determine its maximum height. So this stuff goes back to Algebra 1. You could use your Algebra 1 techniques to find the vertex. That would give you when it reaches its maximum height. Okay, the x value or the t value when it reaches the maximum height. You can plug that back in to find what its maximum height is. You could also use that to find when it hits the ground. You could factor and solve. We don't necessarily have to do that now that we have the derivative, because we also know that the maximum is a point where the first derivative is 0. Now here's the really cool thing. First of all, the first derivative is the velocity. And if we set that equal to 0, we get 48 equals 32t. So t equals 48 over 32. Now, of course, we can reduce that, but give me just a second before we do. Because when we were finding the vertex in Algebra 1, we said that the vertex occurs when t equals negative b over 2a. And in this case, that b is 48 and a is negative 16. That simplifies to 48 over 32, which is precisely what we have here. All of those methods that we learn all connect into this very problem in calculus. Stuff that you picked up in Algebra 1, all of the processes come right to a head here in this problem. So we get that it reaches its maximum height at t equals 1.5. Okay, we know that's a maximum because we know this is a parabola that opens downward. If we were unsure if that was a maximum, we could look at the second derivative and look at concavity around that point. All right, the last question to ask there is, when does it hit the ground? Not a problem we're going to solve with our derivatives. That's just basic algebra. You set your position equation equal to 0 because you want the height to be 0. This is not a factorable equation. Oops, that should be a 432. So your best bet is to either graph and use your intersect feature, or you can use the quadratic formula. Okay? Remember that it's going to give you 2 points. We only want the positive value because we don't care about a negative time value. And so if you do it through, you'll get 3 plus 3 radical 13 over 2. That's when it hits the ground. Any questions with this problem? Now, I have every confidence that if you were given this problem on a test, you could have come up with those answers. You could have come up with a function, the maximum height, time that it hits the ground, without using calculus at all. But like I said, the important part of this problem is not in learning how to do it, because you already have a method for that, but in seeing how the different areas of mathematics are connected, how algebra stems out of calculus, and calculus basically informs algebra. All right, let's just do let's do one more example of finding a particular antiderivative, and then we'll call it an early day. And remember, you're going to have an exam on Wednesday. Tuesday we'll have review. We won't have class on Monday because we're missing 70% of our population. Ooh, that's a good one. So, here's a nice question you might see on the homework or something you might see on the test. Now, you're going to have to listen carefully. I'm not going to write this all in detail because it'll take too long. Given that F passes through the point 1,6 and the slope of its tangent line at any x f of x is 2x plus 1, find f of 2. Now, if you're just looking at this fresh, you might, and just starting without any evaluation, you might wonder how this relates to this lesson, how it relates to 4.8. But remember that the tangent line, the equation of the tangent line is the derivative of the original function. So when we say that the slope of its tangent at x f of x is equal to 2x plus 1, what we're really saying is f prime is 2x plus 1. So take a minute, come up with the antiderivative, use the given information to find a particular antiderivative, and then evaluate f of 2. Okay, what is the antiderivative for this function? Let's just start with the general antiderivative. What is it? X squared plus x plus c. Good. So then in order to find the particular antiderivative, we plug in the point that f must pass through. So if we plug in 6 for our output, 1 for our input, what does c equal? Four. So our particular antiderivative, the actual function for f, is x squared plus x plus 4. The last step, if you've gotten to here, the last step is the easiest one. You plug in 2. That's it. You get 10. So this problem really is just as much a test of the processes in this section, which it's a pretty simple test of the processes in this section. It wasn't an advanced equation, but it's also a test of your understanding of how the functions and their tangents are related. Okay, that's an important thing to understand going into the exam on Wednesday. Any questions from today's lesson? All right.